Hi everyone, this lecture is about the byte ordering in memory for data and instruction based on the little endianness. In other words, I will show using one example how the data segments or the data in the data segment and the instruction in the code segment are stored in the correct order in the memory when using little endian method. First, I will use the example code at the left hand side here that consists of data in the data segment, code in the code segment to demonstrate how they are arranged in the main memory when the computer or the processor are executing the assembly code. So these codes are written in the RISC-V assembly language. During the execution, the data in the data segment will go to the data segment in the memory, whereas the code segment will be stored in the code segment in the memory. So after the explanation on the byte ordering in memory, I will proceed to using the same example to demonstrate how to do the analysis to determine what is the updated content in the register uh, after executing the codes. Because as you learn, after the assembly program is loaded to the main memory, the code segment will normally go to the instruction memory, whereas the data will go to the data cache in the processor uh, to be used during the execution of the program. Then based on the coding given, the register content in the register file here will be updated accordingly. So this how to extract the data from the memory to be updated in the register content will be explained later in the second part. Now let's go back to the byte ordering in the memory. In other words, I would like to explain how the data described in the assembly coding is organized or stored in the correct order in the memory. Zoom in as here, using the concept of little endian. So in some of the RISC-V simulator, we define the code segment to start from address 0. That means the first line of the code segment start from address 0, whereas the data segment start from the address 10000000, which means this data, the first data in the data segment will be stored from the address 10000000. So this is a zoom in of the memory that start from the first address of the data segment. And these are the data described in the coding. And now let's see how they are stored byte by byte in the correct order in the memory. Other part of the memory are BSS that store the initialized variables, heap to be used for dynamic allocation of the memory, and the stack that you use along with the instruction pop and push, especially when the program call the subroutine or procedure. Okay, now let's go back to the data segment here and check out how the data is stored in the correct order. The memory is byte addressable, so that means in each location, each address, only one byte is stored. And in this example, I will describe the byte in hex. The first data is labeled as file 1, and as mentioned just now, we can set it to start from 10000000. So the first byte is 10, so this is straightforward, and it will be stored when the program is loaded. The first byte in 10 will be stored in the first location here. Now let's look at the second variables defined here. The second variable defined here is defined as a half word long. Half word long is 2 bytes. Okay? That means one element here has 2 bytes. Here you see the 4 hex digit, that means 2 bytes. And if you have more than one element, that means the variable described here is an array. When it is stored, the ordering of the element that will go to the memory will start from the first element 2210, followed by second element 1133. Now let's look at the first half word. The first half word, which is 2210, the first element 2210, will first be stored in the memory, okay, after the var1 byte. Okay, so the ordering of the byte, we follow the little endian where the less significant byte will go first to be stored in the memory. So in the first element 2210, the less significant byte is 10. Okay, so 10 will be stored first, followed by the more significant byte, which is 22, will be stored in the next address. Okay. Okay, after we store the first element, we store the second element, which is 1133. Again, the less significant byte will be stored first, which is 33, followed by 11. Let's move to the third variables here, array2. Array2 is defined as a word long. That means in each element here, it has 8 bytes. Okay, 8 bytes mean I'm sorry, 4 bytes. Sorry, 4 bytes. 4 bytes mean 32 bits. So what you need to remember is half word is 16 bits. Okay, and a word is 32 bits long. So that means if we write in full in hex, then there should be 8-digit hex, 8 hex digit. Okay, so 1, 2, 3, 4, 5. If we write it in full by extending the sign, then it will be 0, 0, 0, 1, 2, 3, 4, 5. Totally 8 bytes. Sorry, totally 4 bytes or 32 bits. Okay, so how they are stored? Similarly, less significant byte will go first to be stored. So in this case, 45 is the least significant byte there. So it will be stored first, followed by the second less significant byte, 23, followed by 01, followed by 00. The same go to the second element of the word. So first make it a full, extend it to the full length. Full length means here we have 32 bits or 4 bytes. Okay, then the least significant byte will go first. BC followed by 9A. Why 9A? Because you see BC, 9A, and then followed by 08, followed by 00. Okay, so in conclusion, when you want to show or demonstrate how the data in the data segment is stored in the correct byte ordering in memory, so please take a careful note on the length of each element defined here. Okay. Byte means the val1 has the element of length byte or 8 bits, whereas half means 16 bits for each element, and word means 32 bits for each element. So if the initial value described here does not reach 32 bits, so extend it to the full length before you show how the value are stored in the memory. Next, let's look at the second part, which is the code segment, and see how the instructions are stored in the correct order in the code segment in the memory. That's starting from the address 0000 based on the same concept of little endianness. So because there are many instructions here, so I will just show two of the instructions in detail and two more just the solution about the right location to be used in the memory. First, let's look at the first two instruction. Okay, the first instruction is the AU IPC instruction that basically add the immediate value here, the constant value here, at the upper the first 20 bits of the X18. So in solving this problem, first we need to translate the instruction into binary using the correct instruction format. So if the instruction is AUIPC, it is an instruction under U type or U category. So you need to bring up the format for this U type instruction with the description, the explanation here. Then only start to do the translation of the instruction into binaries first, which is a 32-bit binary because we are using 32-bit RISC-V architecture. Okay, after converting it to binaries, then convert it to the hex before you show how they are stored in the memory. Okay, so first you need to fill out the 32 bits instruction format here. Okay, so the each instruction has a fixed opcode. Okay, so for AUIPC, the opcode is 17 in hex. So this opcode need to be filled up in the opcode field in the instruction format here. Okay, 17 in binary is 00101111. Okay, 17, right? 001 stand for 1 and 0111 is 7, so it's 17 hex. Next, let's look at the second element we need to fill up in the instruction format, which is the destination register or RD in the instruction field here, RD. So what you need to fill up is we look at the actual instruction used in the coding. If the RD refer to this specific register X18, so X18 will be identified as 18 in binary, and 18 will be filled up in this 5-bit field in the instruction format, okay? 18 in binary. Lastly, we check the immediate values involved in the instruction. So in this case, this is the 20 bits immediate value, and you need to fill up the 20 bits immediate value here in binary. So after that, convert it into hex. And because this is a 32-bit RISC-V architecture, so the hex should consist of 4 bytes or 8 digits of the hex. Okay, let's write temporarily here, and I'll derive few more the machine code before we show how they are stored in the memory. Similarly, the second one, okay, uh, we can do the translation of the second instruction, okay, using the similar method. However, this time the instruction is the load instruction, so we need to bring up the right format. Load is under I type. We bring up this format to show the right field of the instruction to be filled up. Okay, so I'm sorry, this is block. This is actually referred to the opcode RD. This is the function tree, the extended opcode bits. This is RS1 and this is immediate value. Okay. So opcode fill up 03 there in binaries, followed by the function tree, the extended opcode bits there 000, and followed by both the registers identity in binaries. RD is here. This is the destination register that will receive the data from the load instruction. So 19 is translated into binaries here, and 18 is translated into the RS1 field. And finally, the immediate value involved here, which is the offset 0 here, will be filled up in the immediate field here. Then translate into hex and put aside first. Okay, now let's look at these two machine code and see one by one how they are stored in the memory. Again, they will stored in the little endian byte ordering. We take for the first instruction machine code, we take the least significant byte, store in the first location of the code segment in the memory, okay, followed by the 090010. Similarly, go to the second instruction, start from the least significant byte to be stored first, okay, 83. 09, 09, and 00. So the third and the fourth instruction is shown with the machine code. I skipped the step to derive them, but you can use the same way of I showed before. Okay, so this is how instructions machine code are stored in the little endian order in the memory. Okay, next, lastly, I'll show how to update the register content. So when given the assembly coding, as mentioned earlier, will be first loaded in the memory, and then the instruction will be fetched up from the instruction cache and go to the components in the processor, the register file, the execution unit, and the data memory if it involves load or store, and then come back to update the register content in the register file, especially the instruction that involve the register. Okay. Now let's look at one by one how these registers are updated. First, AUIPC is to add the 20-bit immediate value onto the upper 20 bits of the X18. Initially, we assume all the registers are 0. So after this AUIPC addition, so the X18 will contain this value in hex, and actually this value is actually referring to the starting address of the data segment here. Okay, because we want to store first the first address of the data segment so that we can use the load instruction to load the data from the data segment. Now let's look at the next instruction, load byte. So please take note, we have load byte, which means we just load 1 byte from the memory to be stored in the destination register, which is X19 here. Okay, so where to fetch from the memory will be referred from this address stored in X18 plus the offset here. So the first offset is 0. So the address, the processor will go and look for the data is x18 content plus 0, which is 1.000.000 is the address where the load byte will get the byte from. Okay. So after you get the byte from this address, then it will be stored as a byte in the destination register, which is x19. The remaining byte in front here need to be filled up by performing the sign extension. Okay. If it is the data obtained from the load byte, then sign extend need to be done when the byte come from the memory to be filled up in the register. Next instruction is load a half word. Okay, so now first you need to find out where is the memory address to get the half word. Okay, so the memory address is coming from the x18 plus 1, the offset is 1. So you do the computation here and you get the address as 100000001. Okay, so the processor will go to 1000001 and this time it need to get not a byte but 2 bytes because it's using the instruction LH, load a half word, which it mean load 2 bytes. So what it will bring from the memory is these 2 bytes. Okay, and when these 2 bytes come to the destination register, so it will be stored based on the return endian concept also, where the first byte, okay, will be stored in the least significant byte as a least significant byte, followed by the second byte stored as the next less significant byte. Okay, and do the sign extend. Okay, this is similar, also load the half word. So half word will come from 1000002. Okay, this is an address you compute from the offset and the x18 content. Okay, so and do the sign extend. The next one is load whole word. That means it need to load 4 bytes, 4 bytes from the memory. So from where in the memory, you need to be computed again using the x18 plus the offset. So we will it will go to fetch from this address, okay, and take this time 4 bytes because the length for the load instruction is a word. Okay, so ordering to be put in the register again, the earlier data will be put as the least significant byte and so on. The last one, it will go to x18 plus 9, which is 100000009 to get how many byte. You check the instruction is LB, then it is just to get 1 byte, okay, which is BC. Okay. However, B has bit 1 at the MSB, so when we do the sign extend, we will have FFFFF in front of the byte BC. Okay, so this is that's why I highlight sign extension is needed if the processor is not fetching the full length of the word. Then when the data come here in the destination register, we need to perform the sign extension. Okay, because by default the data in the register in RISC-V is described in two's complement. Okay. If we need unsigned, then we need to use a slightly different instruction. For example, LBU, which means you want to fetch the unsigned byte from the memory. Okay, so that's all for the explanation on the byte ordering, on how the instruction and data are stored in the memory according to data endianness, and also how to perform the analysis to get the updated content for the registers in the register file based on the given assembly coding. Hope the explanation helped you to understand better. Thank you.